Environmental Test and Design webinar, Hot Enough for You, MIL Standard 810, Climatic Requirements for Military Equipment. My name is Belinda Stashukevich, and I'm the editor of Environmental Test and Design. Environmental Test and Design, which was launched in 2009, specializes in the interrelationship between electronic systems and devices and their environments. This webinar is presented by Steve Ferguson, Executive Vice President of Washington Laboratories. Steve has worked in the compliance test arena for over 35 years at test labs and manufacturing companies designing products, developing procedures, and performing tests. He presents various courses on EMI and EMC compliance. He's an INARTE certified EMC engineer and administers the INARTE-approved Washington Laboratories Testing Center. This webinar today will be interactive. You'll be able to ask questions and answer polls, and we encourage you to participate. Take a look at the GoToWebinar navigation pane. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. Before we begin, we have a poll question for our audience. Attendees, please answer the following question. Should climatic tests be accomplished? Please select one. Before dynamic tests, after dynamic tests, before ingress tests, or on a separate test sample. We'll give you a few seconds to answer. It appears we're still getting answers in. About 75% picked A, and about 20 to 30% picked B. And over to you, Steve.
Well, thank you for that introduction. And the poll question, I'm looking at this and I see a lot of mixed responses. I'm not sure there's an absolute right answer to this. There's reasons to do almost anything. Before ingress testing didn't get selected very much, but there's a reason to do thermals before immersion and etc. in case gaskets seat. There's a reason to see if cracks form after a dynamic test for the ingress, and could heat cause brittleization of materials to cause cracking, so it could be before. Some people look at every item is tested separately. The reality is there's a reason to look at ongoing life cycle requirements. So let's think about this after this discussion, and we'll just go forward. But I'm not sure we have a right answer that fits in every case. With that, let me proceed. Basically, 810 calls for about 8 of the 29 test methods to evaluate the climatic susceptibility. These are listed: the low pressure, the high temperature, low temperature, the shock, the solar radiation, the acidic atmosphere, tough call, but it's an environmental thing, a combined test, and a freeze-thaw thing. The temperature, humidity, vibration, and altitude we'll discuss. Well, we're going to discuss all of them a little bit as we go through today. But we'll discuss how these things combine and ways we can use that. Okay. With that, flow pressure, the altitude test. It's to evaluate material transported, operated, and pressurized, unpressurized aircraft locations, or sometimes at mountaintop locations on the ground environment. Exposed to rapid or explosive decompression could be an item where suddenly the pressure changes, and can this thing tolerate that, your item. It's carried externally on an airplane because obviously the pressures change as we move the airplane and it takes flight. And stored and used in high ground elevation sites. There are several towers that reside on mountaintops, etc. So we need to see how the altitude affects operation. Does temperatures change because of altitude? Does getting rid of temperature cause an issue? A lot of things happen. The seal container may leak or deform. It's amazing to watch a balloon when you put it in an altitude chamber. It grows very, very large. material properties change, especially on these low-density materials where expansions can happen. Overheating because there's little air or atmosphere to be able to get rid of the air heat transfer. You don't move the heat away from an object, so you can clearly get an atom here at a higher altitude. Evaporation, we tend to not think of evaporation, but when it affects lubricating materials, etc., we could have a friction change and cause issues. Seals deteriorate, they may or may not last or maintain the seal because of expansions and contractions that could occur. And corona effect of electrical products, the arcing of high voltages as the altitude changes. So we need to see that the spacing of a high voltage terminals, an RF transmitter or a high power transmitter particularly, for aircraft or high elevation use doesn't get affected. Also discharges that affect the electrical functionality of it. There's 4 categories or 4 procedures for test: the storage, the operation, the rapid, and the explosive decompressions. And in all these cases, tailoring comes into place. By the way, the difference between rapid and explosive is how fast it happens. The explosive changes this altitude immediately. It's a total disregard, where rapid is an open hole or some smaller object that causes it to happen. If I don't have this potential for an explosive or sudden blast to everything, where operation could be an issue, then the item 4 would not become applicable. The tailoring, obviously you got to determine which procedure to use, which ones, how many, and what sequence. What's the test pressure? What altitude do we go to? There's an item in here where pressure becomes involved in an explosive atmosphere environment. Even though explosive is not discussed here, there's an altitude thing that goes on, and we see this request for tests all the time where they specify do this at 70,000 feet. It's not realistic because the atmosphere doesn't support an explosive atmosphere at anything above about 40,000. So asking for this test is not right, and finding a place that can actually try to do it doesn't make any sense to work in an area that doesn't have the pressure. Of course, unless you're trying to make sure you don't get the explosion, and that way you can get rid of all the material that could explode. How fast do you change? Less than 10 meters per second is pretty normal for a change of pressure, and that's an operation or storage kind of item. For the explosive, it can be specified to be very rapid to make not explosive or immediate. Test duration, how long do you stay there? Well, you need to get to a stabilization point. This typically occurs very quickly, but if we're looking for the potential for overheating, you might need to be there much longer. The typical duration in the standard calls for an hour, but clearly temperature stabilization is something that has to be considered. And how are you taking care of the configuration? Is it operating? Is it shipping? And when we start doing these tests, this configuration can be significant because an operating test requires interfaces to support equipment to monitor it and make it work and things of this nature, power, etc. So these cables produce a hole into the chamber. The cables themselves may have to be sealed in order to get this configuration to actually work. A lot of cables can cause the gaps to appear fairly big in between the inside and outside, and getting the altitude right is very difficult. So minimize cables in your configuration. Think towards this, or prepare for a potential sealing of cables if there tends to be a lot. And I'm not just looking at the seal of the porthole that lets the cables go through. I'm looking at the cables themselves allowing leakage. So I have a mesh or a lot of strain reliefs. The shielded cable that isn't shielded or closed at the end will let air gaps come through the various webbing of the shield. Interruptions are typically not permitted. You need to restart the test at the beginning if for some reason you lost your air pressure or you didn't maintain for the duration. So you don't get to say, well, I ran 30 minutes and then shorten it to 30 more to get the full hour of out of. You stay there. The sequences is normally after temperature and dynamic tests or aging of non-metallic parts. We need to see what will happen to this after these things have occurred. Cracks, fractures, expansions of metals, thermal cycling can cause minor gaps that the air pressure, if it's a pressurized container, would not hold, or the seals would give way, and the internal that may be protected would become exposed. So the low pressure test, although it seems kind of straightforward, some of the details get the best of us, and we need to consider how we're going to operate, what do we need to do, and obviously, like everything, the acceptance criteria. A high temperature test is to evaluate some items like circuit stability, overheating, mechanical binding or failure where materials have a different thermal expansion. Shortened life, uneven metal expansion affecting seals where the seals get overly compressed and take a set. Potential issues, clearly dissimilar material coefficient of expansion like between glass and aluminum. If I have these materials with a seal, this temperature expansion changes more dramatically on the aluminum, so I may get a fractured glass if it's being contained very tightly by the metalworks where there's no room for the expansion to prevent cracking, just like we see every day on our sidewalks where the concrete blocks have the expansion joints in there. Lubricant failures, where the temperature allows the lubricant to fade away or not become a liquid, or the cooling back and forth between cooling and heating, the lubricant tends to disappear. The sealant or applied potting, the viscosity may change to where the potting systems actually evaporate in high temperatures. Gaskets may become permanently distorted where you don't get a good air seal anymore. Closures and seals in the same thing. Components. Some components, the value may vary. The operating temperatures for amplifiers and the like may change the gain to where we don't get the performance under temperature that we had at the standard temperatures or the ambient conditions. And outgassing is always a potential. There are many, many things outside of this, but these tend to be the most relevant issues. When I'm looking to do a high temperature test, the procedures are usually storage and operating, limited to that, with a lot of tailoring for the climatic zone. Where am I going to send it? Is it exposed? How long? Do I do a cyclic or a constant temperature? We see in the chart a typical MIL standard. I can't remember which cycle that is, but it seems like it's basic hot from what I can see. But the idea is that we have a cyclic temperature that's applied quite openly. There's also a steady state temperature that people look at as being the aggravated test or more exposed. In reality, most places look at that to be items that are continuously exposed to heated areas, like in an engine compartment on a vehicle, things of that nature for the aggravated or the high temperature steady state condition. The temperature cyclic issues happen. We had an incident not long ago where the cycle test showed up a problem where a temperature test would not. A crystal oscillator became unstable as it changed temperatures, and at a certain temperature it would actually change its characteristics or pop, causing the frequency to shift for that instant or that right as it changed temperature, and it would lose synchronization, so a high bit error rate could occur. So a lot of things are affected that you can find out about running these profiles. So let's not consider a steady state in all cases as the worst case. how are you configuring it in the operation? Is it with things? Is it operating fully? What's the maximum loading? Should we have a full operation? Should we have variables? A stabilization assessment comes into place. How long does it take for the item to get to temperature? So the duration or cyclic tests may never get a stabilization, but the cyclic say, well, our environment's going to change to those temperatures, so whatever happens, happens. So in some cases, you need to make sure that the temperature does transpire to the unit, that it's allowed to operate long enough for everything to be stable, and humidity, if it's could be affected for extremely low relative humidities, you may need to control this. When I have the high temperature work going on, the humidity control tends to be kind of tough to do sometimes. We even had one case, the demands were so harsh, we put one chamber inside another chamber so it could get a decent environment outside so the other chamber could perform. Interruptions, usually an overtest, you inspect it and determine if you need to go, or is it damaged, did we do something that will permanently affect it, usually an undertest. You resume the test where it left off. The sequence is determined in engineering, but usually it's early in the test sequence because it's not damaging, and we may need to have this to identify other failures. So typically after vibration and shock and before low pressure. If it's not married to that, you can change things around quite a bit. The sequence for temperature may need to determine what a high temperature would be during a vibration temperature combined test. So there's nothing solid that says we have this sequence locked in. Your life cycle should talk to the subject. When I look at low temperature potential, we have a similar kind of effect, effects similar to high temperature, but we had freezing and condensation issues associated with it. Procedures are storage and operating, and we had a third, manipulation. Now, manipulation comes into being on low temperature, but not high temperature. Why is that not the case? And I suspect that if we have potential manipulation issues, it could be either way. But typically manipulation is associated with the use of the human interface, where cold weather gear, gloves, things of this nature may need to be evaluated to see that even with those, the human factors come into play during the cold environment. During the hot environment, it's possible to have a similar type issue, but it's not so dominant. In the profile you see on the chart, it's typically bring it down to a temperature like a storage element someplace, and then at some point you elevate it back up to an operating condition, allow it to stabilize there to where you've got the temperatures up to the normal operating mode, and then start operation and use it for its time period until stabilization. Typically this happens in pretty short time depending on the stabilization. This stabilization item that we are constantly talking about, it can be measured. You can have thermocouples, some sort of temperature sensing inside the unit, on the unit at various locations, and have all of them be looked at to say until all reach the temperature, nobody is stabilized. Or it's stabilized when it doesn't change temperature over a short duration while it's at temperature. For instance, maybe you want 3 15-minute intervals where it didn't change by more than 1 degree. So now that indicates stabilization is happening at all points. These are determined by analysis on the equipment. In a lot of cases, the labs get very little information to go by, so we constantly are battling this stabilization issue. Normally, it's a physical look at the mass and saying that in 3 hours or 6 hours or whatever hours, we believe that stabilization will have occurred. It's not as solid as measuring, but it's quite frankly done on a routine basis. If you do get an interruption for either an over or under test, you inspect it, determine if you can go on with that unit or you need to do something different. The sequence, determined engineering, usually it's early because it's normally not damaging. but it does contribute to seals and etc. damage where you can get the effects later. So if I do these early, the later tends to show its head. Typically after shock and vibration and before low pressure, much like the high temperature. Temperature shock comes into being. The purpose is to affect the sudden change between heated and low temperature areas. You've got a vehicle sitting inside a shelter garage in a very cold climate, and you drive it outside and your equipment's exposed suddenly to the low temperatures of a runway in Alaska. The ground to high altitude, quite frankly, things that go on to these high performance aircraft, you take off and you can go from desert heat to extreme high altitudes in a very short time. So you also have the airdrop from heated aircraft to the high altitude where it first goes out. So we're getting that altitude exposure, temperature exposure, etc. All this thing is dropping to the ground, and we expect it to work when it lands. Else there wouldn't be a reason. So for air delivery, same kind of problem. So the procedures call for a hot to cold and a cold to hot method. How long to change between zones? Well, determined in the procedure. Do I do this, leave it stable? When do I get stabilization? What are the levels? Is this an extreme hot, extreme cold? Quite frankly, a lot of chambers have an automatic change the chamber mode for smaller products. Larger products, you typically have to get them from one place to the next where it's been prearranged to have the temperatures, and do this in a short time. When these tests are operating, you also have to consider how you're going to manipulate the cables, because the cables can get very stiff in the cold environment and kind of almost spongy in the hot. You also have to consider how you're going to handle it. If you physically are going to move it from one chamber to the next, can I do it? Can I pick this thing up? Do I have to get it on rollers? How quick can I maneuver it? So in your planning purposes, you proceed to get to a quick environment. Normally they want your transfer time to be very rapid. A lot of large projects allow you a 5-minute window. Smaller ones, typically a 1-minute window, to move this thing pretty quickly. Now obviously the thing has a mass, so it doesn't change temperatures internally immediately. So the idea is to get it into that environment as quickly as we can to see that. Again, under test, restore the operation, continue, and over test you need to inspect it first. The sequence is not specified, but the temperature test may indicate a sequence need. So if I've got my high and low temperature work, I may need to consider whether this is done in conjunction with the other or dynamic tests or other climatic tests that could come into being. I have another question here.
Attendees, please answer the following question. How do you decide on constant or cyclic profiles? Life cycle plan, deployment conditions, installation parameters, or test procedure? We'll give you a few seconds to answer. We're getting a few answers in. A few more seconds. Slight majority said B, followed by C, and then A. Back to you, Steve.
Okay. The life cycle plan is used to determine what to do. It should be based on deployment conditions and installation. Your life cycle tells this is how I'm going to use this product, where it's going, its thing. That life cycle plan should develop into the procedure that gives us specifics on how we're going to evaluate that. So all these things really combine with the life cycle plan being the dominant structure if you can get it. It's a highly avoided kind of product, but obviously it evolves into test procedure, and once that is written and approved, that's where we're going to go. So decisions, if I've got a test procedure written and approved, clearly that's the answer, it's done. If not, I need to consider this lifelike arrangement and develop a plan, whether it be formal or informal. Solar radiation testing now takes the direct heating effects. It's a lot like high temperature, but directional with thermal gradients going on. The actinic or photodegradation effects of fading and deterioration of polymers and elastics and elastometers, various things where the actual solar or the infrared lighting, the full spectrum lighting comes into place to simulate sunlight. Procedure is typically a cycling thing, but we could have a steady state condition going on. The tailoring, you need to select a procedure. What am I going to do? Cycle it, test levels. The number of cycles, quite frankly, 7 days is typical, 3 days is used as an alternative when it's not exposed frequently. If it's exposed frequently and for long durations to the solar, it's mounted on a vehicle parked outside, these cycles shouldn't be shortened terribly. If it's mounted inside a vehicle, the heating effects get there versus solar. Unless we go in and out with it, we're exposing it. A lot of times the testing involves heating and the solar radiation. Sometimes the plans allow the solar radiation to take dominance and take the heating effect also. You need to consider any temperature, humidity profile there, how you're configuring it. Is it shaded? Is it in a container? Is it in a bag, carry bag or something like that? Interruptions with an under test, you may consider the test complete or resume it, depending on how far you are in the performance of the product. And an over test, you need to see if you've physically damaged it. The sequence is not prior to vibration. The vibration tests tend to cause these things to be exacerbated. So you need to do that dynamic test prior to the solar radiation. The acidic atmosphere, by the way, the solar radiation tests have the same kind of effects of the temperature, except we've also added the photodegradation. Didn't want to misstating that. For the acidic atmosphere, we assess with the withstand capability for corrosive things, surface finishes, metal corrosion, pitting, cement, optics, things of this nature, or your camera, your glass, your viewing areas tend to get all these blotches from this acidic things. Procedure is similar to salt fog or spray, and you can use a salt fog chamber, but again, once you do, you may not be able to get back to salt in its purity because of the acids. Typically, the sulfuric acid is used. The applicable procedure, you need to determine what you're doing. If I'm looking at a spray or a fogging mist, how long? The duration is 3 2-hour sprayings with 22 hours of storage, basically 3 days. Or you could have 4 2-hour sprayings with 7-day storages each to allow the effects to be shown during the drying period. So when the exposure happens, these things happen a lot in areas where the contaminations, or it's used in places where there's a lot of contamination in the air. We see it from coal burning plants, power plants, where the contamination of the air, the smog dominates. We see it in a lot of cities where the smog is dominant. We can see it in any number of places, but we need to see what effects this will have in the life cycle. We travel all over the world with these products and have them in all kinds of places, so keeping them outside of this environment is not very likely. But the test isn't done quite often because most of the time the product says, well, it's a cover and it's not really going to affect everything. It will erode, and we know that, so we allow it. Unless it's exposed to a heavy environment like this test is seldom called out. Test configurations could be packaged. It could be a protected environment where I'm putting a shelter around it. It could be a deployed state where I've got it out in the open, like an antenna that's exposed outside of its radome, for example, depending on its application. The under test, we typically inspect it, evaluate it, and restart at the interruption point. Once you start doing this, the accumulation of the damage is continually there, so you don't restart from scratch or you'll really severely overexpose. When you do an overtest or it's more heavily acid content than we should, you can hold that item until you get an evaluation. If it's determined that the interruption did no damage, you can restart at the interruption point. Again, you don't go back to the beginning because this has a lot of cumulative effects. The sequence is typically after a humidity environment or fungus environment, before sand and dust or other tests that affect protective coatings. Now, some people say fungus affects protective coatings. No, not typically. Getting rid of the fungus does that, but if fungus test is done, you can do this beforehand. Quite frankly, the fungus test is done on other samples or items that are pretty much separate, even coupon samples, so it usually doesn't get into the fray of being a before or after. The temperature, humidity, vibration, and altitude. This combined test looks at a lot of things. When I look at it, you typically don't try to get all four things at once because, quite frankly, at high elevations, the humidity doesn't get there. The temperatures get exposed one way or the other, so you can do this. So vibration and temperature, quite frankly, get together. Temperature, altitude, and humidity, but again, you got to look at the humidity to make sure you don't try to go so high that humidity can't exist. Humidity and temperature is a combined test, quite frankly. And the standard clearly states this is not intended to replace individual tests, but a lot of profiles call for doing it this way and not doing the individual tests. Something for you to work out with the customer or the user to make sure that they want it all done. The procedures call for engineering development, and quite frankly, we're going to hit on the next slide or two a little bit more on that. Or flight and operations support. This is a dominant thing in the flight or vehicle use, and quite frankly, qualification testing. Could call these things out. We really want to see how the combined effects happen during development. Qualification should see a piece of it, but if development has supported it well, the plain test without the combined effects can be used for qualification. The tailoring needs to happen and define the purpose. What am I trying to accomplish with this combined test? The test parameters need to be selected to accentuate any stresses, and the profiles need to be provided for a combined test suite. The interruptions are done from the individual test methods in the sequence. You need to do vibration first if performed individually. This kind of thing is quite honestly, it supports HALT testing. It's a good basis for a lot of HALT tests, where HALT is a highly accelerated life test, where combined effects and extremes. I put a sample profile. It's not by any means the end of all things because these require a lot of engineering development to get a good profile. But this happened to be one that was worked up for a product. And doing these kind of things, they've been shown to identify up to about 95% of issues in one day of HALT testing that could be found over 3 to 4 weeks of qualification testing. So we're going to do some things. We're going to get some temperature extreme things going on early with vibration out of the equation. We're going to cycle it and hold it for short periods at extremes. Did this happen? Did this happen? We constantly are looking for what occurred. Try to go way beyond what the life cycle is going to go for. I think this went to minus 30 degrees C is what we recommended for this, and its anticipated life was at 0 C. It's an office piece. So the idea was to try to identify things by taking it to the limits, way beyond the limits. And once I identify the things, we need to do analysis on what it told us. So HALT testing without the analysis is not worthwhile. As things occur, where did it occur? At what temperature? Was it after vibe, before vibe, in conjunction with vibration? These questions need to come up quite honestly at different levels. We're taking different vibration levels while we change temperatures. So we stay there a short duration, get it to the next place, do it again. These combined effects accentuate problems where you can clearly start identifying and do the fault analysis. This was clearly that. Once the fault analysis removes these problems, or identifies and the modifications happen to remove the problems, the HALT test now served you well in a very short time to say, I've got a likely issue. That would have showed up during qualification tests, but it could have taken a long time to get there, not when you need to find it 3 or 4 weeks into an overall test program and have to restart after redesign of these kind of issues. So HALT testing gets pulled into play a lot of ways, and there's a lot of thoughts on this, but this is the area that I've seen more people kind of use and have success with than most any other method. So I tend to think this way from not just our own experiences, but from several different organizations that base HALT testing on this manner. Another poll question.
Attendees, please answer the following question. What methods are used to determine temperature stabilization? Thermocouple on the test sample, time allowance, not necessary for cyclic tests, or all of the above? We'll give you a few seconds to answer. Looks like a pretty overwhelming majority went with A, thermocouple on the test sample.
Well, I tend to agree. That's the best way, and the problem is figuring out where on the test sample. Can it go inside or should it go inside? Seal units don't allow me to. So sometimes I'm just stuck with the time allowance to say, even though the chassis may have changed temperature, do I need to allow things inside to stabilize? And I don't have any other way on a sealed product than the time allowance. Is it necessary for cyclic tests? Maybe not. We may not even need to achieve it because the cycle test is going to run through based on exposures to the environment, and the environment's telling us how long to stay there. So I guess all of the above could be a useful tool. You can't eliminate anybody, so all of the above has to be under consideration with, if it's available, thermocouple on the sample at an appropriate location is the preferred method. So I agree with the majority in that respect, but don't think it's the answer that's going to stabilize everything. The freeze-thaw test methods. The purpose is to identify the effects of liquids changing to solids on the material and moisture by climatic change. Things get a little bit moist and you get a little bit of freezing. So it's right at this ragged edge of staying frozen and thawing out. So we're constantly changing its environment. When these things happen, these expansions cause the moisture to creep in because the thermals have changed the material, and then the liquid state can enter when it gets to that place because the cold has kept the thermal expansion to where gaps may appear. You may need to cycle it above and below the freeze point, getting to there, the deneural effect, fogging or the transfer from warm to cold. The glass, the lenses, etc. fog over because I'm right at a place where I can accumulate a moisture and tend to freeze it over where my camera, my visual stuff goes away. And these rapid temperature changes from hot to cold and back to warm, where they happen very suddenly in a freeze-thaw where I've got moisture involved or liquids involved in some respects. The tailoring has to be the configuration. Do you have protection? Is it operating, etc.? Temperature ranges, where are we at? How much above and below am I going to allow this? And do I need to allow it to stay there very long? So those are things that come into place. The sprayed moisture, how many times I need to do it? Quite frankly, things that are exposed outside get a lot of cycles involved. The interruption is always a reestablish the conditions and resume it. The sequence is not specified, but typically after tests where the seals could be damaged, any of those things where overheating could cause a seal deformation or pressures, climatics tearing things or causing the temperatures for liquid seals to deteriorate. A lot of reasons call for this test. Again, it's those things that have a tendency to be exposed to this type back and forth environment. If we look at systems that are ground-based, these things happen because they're outdoors, but almost all of 810 are not ground-based tests. So tailoring it becomes even more important here for a ground-based situation. Almost everything in 810 is dealt with on a vehicle or aircraft or a ship or some moving or functional thing that changes, seldom on ground environment activities. The tailoring, obviously we've looked at these things and everywhere in it tailoring was discussed. We need to develop it based on some common sense for material and application. It doesn't make any sense to do tests that have no application whatsoever. If it's never going to see that and you do the test, if you fail, you're setting up a have to correct mode. So not doing the test makes all the sense in the world, or else, oh, it failed, but it was for information only. Unless that's clearly stated, it's just for information and pass-fail doesn't apply, it can get you into trouble for a redesign of the product. The details of the evaluation and the methods need to be thought of real harshly. How am I going to get to where I'm getting? Combining tests, the method 520, the temperature, humidity, vibration, and altitude come into place. Any special conditions that come into being need to be brought forth. Quite frankly, a lot of products get quoted by the test lab. They've never seen the product. They get a request for quote or some parameters. They ask the questions, how big is it to make sure it'll fit? How do I power it to make sure they got some electricity for it? And they go ahead and quote the test. Then the item suddenly shows up and they look at it and say, what have I done? I need to really consider, because the test is not going to tell me anything. You need to plan for vibration and shock particularly. In conjunction with all these climatic tests, vibration and shock need to be mixed into those things at the right places. You may have to get some fixturing involved here. How do I handle cables for thermal shock? How am I going to get cables in and out for thermal shock, or any of the climatic tests? How do I enter and get out of the chamber? Need to get some details on the methods, controls. And then the problem with the tailoring is you need to get somebody to accept it, to agree that this tailored process does meet the intended requirement. This tends to be the hardest part of the overall situation, getting buy-in. You need to get a test procedure here to cover this. The life cycle control environmental profile needs to be out there, but it's typically a very elusive document. We in the military groups are faced with the same problem as everywhere else. We're trying to buy commercial off the shelf or COTS equipment. Things are already in play that have no or very minimal environmental control, and then suddenly we want to make it go everywhere. So quite frankly, the worst case is often stated. The manufacturer is funding this thing on his own, and he says, I want it to go anywhere, do every job in the whole world. Then he gets the price going on and says, well, wait a minute, maybe we need to consider reality. So this test procedure formulates an agreement. This is what we're going to do. It's documenting how the environment, how we're going to evaluate it from the conditions. It could have a reason why we're doing it that way. What's the sequence of testing? Do we know this? The manufacturer and the user have the scope clearly defined, and the lab knows what they're expected to do and what the pass-fail criteria is. Procedure should have the escape clauses, so if something does occur, how do we get out of it? For instance, a one-time bogey that just kind of went haywire in the test and we don't know what caused it, and it won't do it again. So we need to configure those things. And when we deviate from the procedure, because when we see the item for the first time, we realize, oops, we didn't mean to go in and test it this way. And quite frankly, these procedures are reviewed, but the understanding of what's going to happen isn't as clean as it needs to be. The instructions are in the procedure, but the idea is that the people may not combine, the lab knows what it means, but they don't know the product. The product knows what it means without knowing what the lab's going to do to it exactly. So when they start seeing these items occur, they say, no, that wasn't the intent. So how are you going to process a deviation? Who's going to sign it? Who's going to allow it? Who's going to fund it? Because suddenly a process change could cost test dollars. So consider those in developing the procedure. You need to get the acceptance down pat. The pass-fail criteria must be clearly defined, measurable, and have the equipment to do it. All these things need to be coming about. And I use this particular slide in a lot of things because it applies not just for environmental tests, but pretty much anywhere you can imagine. Without knowing what the pass-fail criteria is and how we determine that we are in fact within those issues, we get a lot of mixed things, information-only things. How you get requests to test a failure, to test this level and it breaks the first time. These really need to be looked at, and quite frankly, somebody proceeding with a test without knowing what the acceptance is scares me. They're not looking at it realistically. They think it's just going to become obvious that it's going to do something so dramatic it's obvious that it failed, when it may not be the case. We also need to get the measurement terms defined. That, the average individual knows what the difference between 1 and 10 is, but did you know that 3 dB is a ratio of 10 to 1? Could be, depending on the log function. So you may think 3 is a very small number, but if he translates it into linear numbers, it could be a very large number. So decibel might need to be understood, where a lot of people may not understand that particular subject. So when we're handing it off to the people that are actually executing, see that they get the information necessary, that there's a clean way to say, yes, no, we're doing well, or this is not acceptable. Test acceptance, the function needs to be, are operational checks going to be made? How often? So I may have to run a complete acceptance test procedure. We may see measurements that are there while we're doing this. Does broken glass constitute or practice structural cracks? Connections, how much is too much? So the test acceptance is there. Do I get a salt fog environment or acidic environment where I'm starting to see corrosion on the connector shell, but the pins are fine? Is that okay? Maybe a problem where I've suddenly got binding and jamming. I can't take the connector off when it's warm. That could be an issue that would prevent service. And how tests influence subsequent tests. If I've got a unit coated in dust, the salt may not adhere to it, okay? And if I've got a test that's done with sand abrasion, now is the corrosion going to happen from the salt test? So we look at the sequence of tests and saying what will contribute to the next, what's their life cycle. If it's going to be taken out in the sandy helicopter pad and exposed to all the sand blasting away, then taken to the beach and used on the salt fog environment, then that's real, but it's not, frankly, often. Loose parts. How loose is loose? Do we open the unit and go and see if the nuts came loose? No, not typically. You have to look at what becomes acceptable. Rattles and shakes that weren't there when we started. We might need to look at these conditions to make sure we're there. Okay, influence on subsequent tests. Another poll question.
Okay, attendees, please answer the following question. How do we determine the test duration? MIL Standard 810G specifies the duration for each test. Test procedure defines the duration. Life cycle analysis or deployment locations. I'll give you a few seconds to answer. We've got some answers coming in. Appears to be the first three seem to get pretty evenly split, with C life cycle analysis leading by a bit. Back to you, Steve.
Well, okay. Life cycle analysis is the answer dominantly, but that should get into the test procedure, and the procedure is going to specifically talk about these things. The life cycle tells us what to put in the procedure. 810 seldom puts a duration. It gives options for durations and suggestions, but it's not real for the product. So we tend to avoid that. And deployment locations could affect it, but that's going to get into the life cycle analysis. If we have the life cycle analysis, it's the way to go, and it supports the procedure where it's really gets documented. There are a lot of other standards involved in the climatic states along with all the environmental modes. The IEC 6068-X series has a lot of specifics. The DO-160 for commercial aircraft, a variety of special applications. Railroad systems have a series of documents, SAE documents, a lot of places for vehicles. But if you look at any of them, they have a common theme, tailoring and life cycle considerations. I think that that's something we need to consider throughout our work in the environmental test, that tailoring and life cycle considerations should always be in the forefront of what we're doing. Make sense of the project. That concludes the presentation. Did we receive any questions?
Thank you, Steve. We'd like to have a call for final questions from our attendees. Please enter any last questions you may have in the navigation pane. We have received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, www.environmentaltestanddesign.com. You can also email us at info@etdnews.com with specific needs, and we can direct you accordingly. Steve, here's a question for you. What standard presents the HALT profile you showed?
The HALT profile. It's not really defined in the standard to my knowledge. It's something that's worked out with the engineering and the product specifics to look at where we're at. That HALT profile or something along those lines appear in a lot of papers that have been presented over the years at symposia and articles that we see in various publications and online. So it's out there, and the common theme is something in that kind of profile, but the exacts are worked out based on the product specifics.
Okay.
Anything else?
Another question. Do you normally install thermocouples to assess thermal stability?
Quite frankly, we don't normally. A few profiles, those that have been worked out really well, and assessments call for this, and we do that regularly. Usually they're involved in well-defined programs, but a lot of people come in with poorly defined programs that don't know what it means, and suddenly we're at the last minute. Also, the ability to install those in the sealed items doesn't get to the inside very much. And I'm a firm believer that if I'm running the cyclic profile, I'm going to run that profile no matter whether stability gets there or not. So the thermocouple just simply gives me feedback on what happened at that particular function. It's nice to know, but some people just don't require it. Anything?
Here's another question. Test fixtures are commonly used for vibration and shock tests. Should they be included in the temperature test?
That's good. Test fixtures typically don't go there unless it simulates an installation. If the fixture, like for instance, we're mounting it on a plate in a vehicle, where that plate's mass is going to cause an effect on the small sensor, we may want to get a fixture in there for the climatic tests. In general, the fixtures may not need to be there. If we're testing multiple samples of something, there may be a fixture to contain them, and the fixture needs to avoid influencing the test. So if we've got something that hangs out in the air and we mount it to a hard object, it can cause ill effects because it dampens the transition of temperatures and the like. So a fixture is a tough call. We sometimes need them to make it work, and we have to design it to avoid influence, and other times we need it there so the influence of the real installation is considered as part of the overall profile. That was a good question. Do you have anything else?
One more. We have received, oh, excuse me. Actually, that's it. We have received
Okay.
so many great questions that we will try to address in the future. Steve, thank you again for your time and expertise. Webinar attendees, if you have any more questions we didn't answer here, please send us an email at info@etdnews.com. A recording of this webinar will be available on our website, environmentaltestanddesign.com. We will also send a link to all participants shortly. Thank you for attending.
Thank you.